Yes, Lecture.
Hi, are you joining the class?
I don't think it's too trivial for you. But yeah.
No, I think there was a mistake in the schedule. Yeah, I didn't realize this room was double booked. 410.
Oh, really?
Yeah, I can.
So you
Yeah,
have
I
a
should-
class to teach here?
Yeah, as exactly Tuesday and Thursday. But I think I should
How
be
many
fine.
students in the class?
Unfortunately, I only have one.
Okay, so then maybe the conference room?
Okay, yeah, I can use that room.
At least today.
Yeah, I should double check the schedule.
No, I think the schedule. Okay,
Okay, no problem.
Okay, thanks.
Okay, good. Enjoy the class.
Should be
Missing two.
two of us. Right, Abdullah and
Mine.
Michael. And Alia also said she will be enrolling in the course. She's not back in town yet. Let's- Okay. This. So this time I teach two different groups, and then you have to do this every day. Please let me know. Did you guys start the home? Michael? What's the purpose of that?
No.
Is that just stuck there? Or is there a purpose? I cannot even reach that, so I won't even try to. Okay, how's the homework going? You guys check it? Arjun has completed it, he submitted, that was good. If you have quizzes, again, will be due in the next class, or before the next class, so if you have, but if not, in the next class, that's try to see on a regular basis. Let's try. This. Homework. Homework one we said is due 25th. Tuesday. So that's next class. So usually I try to spend 2 lectures on Newton's law. So we lost because I got sick, one of them. So I'll try to do that today also. primarily an example on velocity dependent forces. But before that, I should finish whatever we were doing last time. I pretty much, I would say, did not mess up anything, but I think I was in a hurry to make interpretations and got confused with myself. So nothing went wrong last time. So let's very quickly go over that. So we were doing position dependent we took a special example. So you have mass times acceleration, which is derivative of velocity with respect to time. And we said this is only dependent on position. In fact, we made it just a one-dimensional problem by saying that we'll be interested in a situation where we have a planet and something is falling radially inward. So that's mass m, let's say that's capital M. And we also said this could have a radius r. That doesn't play a significant role unless, as one of you guys said, unless you come and hit on the surface itself. And the interaction energy is given by the Newton's law of gravitation, and you get m times. In this case, everything is going radially inward, so I can say it is a one-dimensional problem. So that's dv by dt, where dv is r by dt. So there is no tangential component in the motion at all. And that's equal to, it is going inward, so it is minus of g m over r squared. And where the directions I have taken care of. Did I get the sign correct? Let's see. How can I check the sign? So acceleration is downward, correct? Yeah, so this is acceleration, so that's downward. So I think that's correct. Minus. Correct. Okay. That was our problem, and we said this is m cancels out, and to work this problem out, we multiplied by velocity, right? So that's dr by dt. So we have v dv by dt is equal to minus gm over r squared times dr by dt. That was idea. We said immediately that this is derivative of half v squared. That's sort of the kinetic energy showing up, and this is equal to probably negative derivative of gm over r. When I take a derivative with r squared, I get a minus 1 over r squared, so it's plus, I suppose, correct? And it's plus. And we learned that this is a constant, so that makes this time derivative of kinetic energy, potential energy, remember, as a minus, but when you bring it to the since you're taking it to the right, so it becomes positive. So this is minus of gm over r is equal to 0. So you interpret the inside part as the energy after you multiply the m. So it is good to say that you multiply the m there because it's 0 anyway. So you say, so there is a constant of motion, often we call it. So that's Gm over R is equal to T. And then we wanted to have a very special scenario where we said it starts from infinity. So special case, and that was for simplicity. So we said at t equal to 0, it is all the way and at infinity. So position R is at infinity, and at t equal to 0, its velocity is equal to 0. So it starts from rest all the way from infinity. And that leads to the idea that since energy has to be a constant,
No, it's the load, the mass of the object, doesn't that go into the,
second term. Is that? Right, thank you. Yeah. I meant should multiply both terms, of course. Damage. Yeah, sorry. So that so if we have this scenario, then we know that at this point, what is energy? Velocity is equal to 0, and the potential energy is also 0 because at r tends to infinity, that goes to 0. So energy is equal to 0. If it is 0 to begin with, it stays 0 all through, and we learn that velocity at any time then is half mv squared is always equal to t mm over r. If we cancel this m out, we notice that v square is equal to 2 times gm over r. That's what it is, but it can also be written as nicely or over r square times r. And you might see that if you had uniform acceleration, you have what is velocity squared. So if uniform acceleration case, what is velocity squared? If you start from rest, that means on the surface of Earth, I drop a ball from rest. What's the velocity it will pick up as it falls a certain height? Let's say, what's the formula for that? Velocity squared. Is that clear, my question? 2g, yes. 2 times change in height times, so this is 2gh, right? So that's your formula. Here we are not having uniform acceleration, but you still see that this is the acceleration, right? Gm over r squared is the magnitude of the acceleration. You still get that structure there, but now it's a position dependent acceleration, and you still get that form intact. So it is just a chance. So that's one thing we can do. But last time, what we were doing is we didn't go into this. What we said was we started calculating the time. How much time does it take to fall all the way from infinity to the, which also you can actually invert the problem and say that how much time will it take from anywhere, start from a certain point, and if you were to throw it in the inverse direction, how much time does it take to reach the surface of the universe, if you want. So let's do that. So we will let's begin from here, let's say, right? So this is dr by dt square is equal to 2 times GM over R, and take a square root on both sides. This becomes square root here, and R, let's say, so the square root of R, and then 1 over 2GM. It's equal to dt. And again, we can say we integrate this on both sides. So we can start from time t equal to 0. At time t equal to 0, it's all the way at infinity. So this is R is equal to infinity. And at some time t, it reaches some position R. And it doesn't matter where you are. So you start from here, and then you reach a little down there, or for that matter, you can go all the way to the surface of Earth. That's either a problem. And the time it takes for that is t minus 0 is equal to 1 over 2gm. This is infinity to R square root of the R square root of R. And that's infinity, right? That is the R in the numerator, whatever you do. So it's going to be infinite. We can have a structure for this. In what form is it going to infinity? But the answer is an infinity, which means that, and more important, first example we can think of it as it starts from here, and how much time does it take to reach the surface? And again, you can invert the problem. You can say that I throw something from the surface of Earth. Typically, we say, what is the escape velocity of a stone to reach all the way to infinity? And it is actually infinity, right? It will take that much velocity to reach that. But then if you ask, how much time will it take? It will take forever, right? Just to reach that case. And that's what I started struggling last time, that oh, this is not okay. But this is fine. And but then more dramatic is the situation that, okay, from here it seems like it's very far away. What if you're really close to the edge of the universe, let's say, and what does it mean to say, oh, very close? If it is infinite, every point is far away. And that's exactly the point, that every point is very far away from infinity. So it doesn't matter where you are, if you want to reach that infinite, at least if you want to reach it with 0 velocity, it will always take infinite time. This shows up interestingly in other places also. So let me point this out. So let's ask the question. So you have a hilltop, like this is a mountain like structure. If you want an exact form for this, let's say this is y is equal to half x squared. Just a parabola structure there. And again, that is gravity acting downward. Let's say uniform gravity acting downwards. And this can be a quiz problem, just for analysis for your sake. And let's say you start from here with some velocity v. And it is just barely enough. So the question is, how much time will it take for this ball? And your goal is to just barely come and stand here. You cannot cross it, because at the moment you cross it, you will start going the other way, either way, right? If you don't reach the top, then you come down backward. And if you cross that top point, it'll go through. But the question is, the goal is to reach right on top. Like it's a very sensitive point there, and calculate the time for that. Of course, if I ask you with what velocity you have to go, you will immediately say this, right? Oh, I know the height here, and you will calculate the velocity. But the point is, how much time does it take? It doesn't matter where you start from wherever you want and reach the top, and you have to just barely reach the top. And if you calculate the time, it doesn't matter what potential this is, this will always be infinite. The same challenge that you approach here. And this is well documented. This is called Sojourn. I don't know how to pronounce this. Anyone knows how to pronounce it? It's a French term. Just take it.
It's just sojourn.
Okay. Sojourn. So look it up. So look it up and do the small analysis just for fun. Like it cannot be uniform gravity. Just analyze that, and it is surprising that it doesn't matter where you start from, and you will see that T will come out to be infinity. Very similar to what is going on here. Any comments or questions? Yes, please.
That's a question for T. It's mathematical infinity, not physical.
Okay. That's a good question. Okay. What do you mean by mathematical?
Absolute infinity.
It is okay. Maybe I'm mixing up words. It's absolute in the sense that if I really try to reach there, it will take me infinite time. In that sense, it's really physical. Is that?
Sometimes we use infinity as big, for example, very big distances compared to the radius of our planet.
Correct. Here I would say this is physical. I would say again, it might have to do with what's the context in which you define this mathematical and physical infinities. I know it because you often subtract these quantities and say that these are unphysical. But I don't see how you would subtract this, because this is really, if you were to interpret this, how much time does it take? It will really, it will be in that particular sense. It is physical, I think, personally, but I'm open for criticism. Maybe that's the way to put it. Since you specifically said it, maybe you have something in mind.
For example, the end of the solar system compared to the radius of the planet can be infinity.
Correct. Yeah. That's also infinity. Yeah.
But we can reach that distances.
Yeah. Okay. We cannot reach those. Right? Yeah, infinity cannot be reached, right? So I would say.
This is absolute infinity.
No, I would say this is physical in the sense that there is a dimension associated with it. And you can actually keep, you know how it will grow also. It will grow as a power of R. There it is what? 1/2 plus 1, 3/2 power. So I would say it is really physical. Typically, sometimes what you say is unphysical is when it is dimensionless. And you know that, oh, this cannot exist. This is only a coordinate, like some mathematical structure came in, and or often you say it is a spurious infinity, in the sense that in the mathematical formalism that you're using, you had to introduce something and you couldn't help but introduce an infinity. So you introduced it, but then it has nothing to do with physics. At the end, it has to go away. And often it doesn't go away because you don't know how to throw it out. So there it is not physical, but here I would say this, if I were to choose between the two, I would say it is really physical. Yeah. I would think it is really physical in mind. But again, infinities are very sensitive. But this seems to be a simple infinity. That's the way. So this is a simple infinity. It makes sense, right? Yeah, it takes that much time to reach there. And again, another example is so similar example, right? I think I might have told this before. If you have a point and you have a pendulum, simple, right? One of very early in introductory level physics, we give this example again, uniform gravity, and we say this oscillates, right? So this oscillates, and that's your angle phi. It, let's say, it grows in that direction. Usually, very quickly in the early introductory level physics, again, we say this small angle approximation, and then we get a simple harmonic motion. But let's not do it, because once you make it small angle approximation, it cannot go beyond certain points, right? So we said, okay, no, we don't want to do that. Let phi be complete, and then it can again be solved. Like it doesn't get solved in simple sine and cosine functions. Instead, you have to solve it in terms of what is called elliptic integrals. But at this stage of our mathematical background, we understand that reasonably well, or else you can look it up and it's really understandable. And then you can again ask, okay, that's good. Now I know the complete solution for it. That's very nice. But how much time does it take if I were to make it go all the way to here? So I can drop it from here, and then it goes there. That's time period, right? So that's t over 2 for small angle. But now let's say I start from the very top, as close as possible. Again, that limiting form, I had to talk about that limits where phi really goes to pi by 2. And then I drop it, it goes all the way and then comes back. And you take the limit to pi by 2, that comes out of infinite. It is not a finite time period at all, it's infinite. I would say that's physical. I would call it physical. And I think from what I gather between physical infinities and mathematical, I would think this is physical in that sense. But again, criticize. Right? Could be. There could be more subtle definitions of physical and mathematical. So yeah, good point. So, any other comments? Yeah, that's the best I can say there. Okay, so that's some. That's an example we have for position dependent. Most of your homework is velocity dependent forces, and two of the velocity dependent forces we have is one is or the classic ones is one is force under a magnetic field, and the other is a Coriolis force. If that is gravitational, if you're rotating, that's also it has a lot of similarity there. So it's good to just at least do one problem. I'll do the simple case of magnetic field. Just do it as a differential equation. Is good. It's a good exercise to go through, where the differential equation, there are two differential equations, two boundary conditions. Probably you have all seen it at one time or the other. Otherwise, we just go through it if you've never done it. Often I do that because often we take it for granted that it is going in a circle and not bother about deriving that. So we'll just do that here. It's also useful in the sense later on, one of the classic examples I'll keep alluding on again and again is this case of electric and magnetic field example. It's good to go through that. And from next class, we will start doing the variational calculus, which we will use to do the Hamilton principle and the Lagrangian principle. So let's do a velocity dependent example force examples of velocity dependent And this mass times acceleration is dv by dt is equal to, no, let's switch off the electric field in your homework, you would switch on the electric field. So it is, we just do q v cross v. In the last lecture, we said if we have a position dependent force, and if that force is a conservative force, then there is a potential energy associated with that. Right? And there are very few examples: electrostatics, gravitational force, and the spring force also comes into that picture. What about magnetism? Right? What's the potential energy associated with a magnetic field? Is it a conservative force? Is the magnetic force a conservative force? It's a harder question, so I'll leave that for it. It's a little harder question to answer. Should I change the? Okay, so the question is magnetic force conservative? I think, yeah, you guys have done electromagnetism with me, right? So I mentioned it there, and you spent one lecture deriving the expression for it. But then the question is, what is the potential energy, and is there a potential energy? But be careful in answering that, because the way this is posed, it seems to say that, oh, that's the only possibility. That's a subtlety. The hint is that what about momentum? Right? Think about momentum, or even a better, right? Maybe P. You might have seen this, or maybe not this. Is P is equal to mv? Is P, is the momentum always equal to mass times velocity? And the answer is no. Momentum is not mass times velocity all the time. Only in position dependent forces is it mass times velocity. If you have velocity dependent forces, then this changes. So then you call it what is called a canonical momentum. So we'll have chances to see more of that. For now, this is a quiz, right? Explore that. And I do address that in my course. So, okay, so we want to do, without worrying about that, we just solve this as a differential equation, right? It helps to get rid of some variables. Let's say this is dv by dt. It's equal to, let's say, v crossed with omega, where the vector omega is q times b over m. And what's the name for that? The special name you give for this definition, a matter of definition, but anyone remembers what it's called? It has a, what's the dimension of omega? What's the dimension? Per second, right? 1 over time. And in fact, omega seems to be angular frequency, it's radians per second. So that seems to say this is an angular speed or angular frequency. And this is the angular frequency. If you have a charged particle going in a magnetic field, it goes in a circle. And this is the time period or the angular frequency. How many times does it go in a circle in a certain amount of time? And that's a name associated with that. That angular frequency has a special name. It's a very popular.
Cyclotronic.
Yes, cyclotron frequency. Correct. Yeah, so that's almost a fundamental, very fundamental. In sense. Often, this is a dimension, right? So it's 1 over time, and yeah. So second quiz, right? This is 1 over time. Like the dimension is 1 over time, and if you're in relativity, you have what is called time dilation. Right? Time takes a little longer. Go and remember that that time has to be in the direction of your, or time doesn't have direction, right? How do you say? Yeah, time dilates. It doesn't matter, right? So time just dilates. If you're moving, you tend to be why am I getting confused? Sorry. So yeah, you will be younger if you're moving, correct? That's the basic idea. So think about the time dilation in relativity and then ask, this is also a time, like it's an inverse time in a sense here. And you ask, what happens to the cyclotron frequency if you were to accommodate for relativity? Right. So now you said you're doing relativistic physics. How will the cyclotron frequency change in a relativistic problem? You say that, okay, I want the correct cyclotron frequency, not a non-relativistic version. And look out and see how this transforms, or what is it new cyclotron frequency, and does that match with the idea of time dilation or not? Check it out. So, what cyclotron frequency is it relativistic? Okay, so that's for the parameter omega that I introduced. So now there is only what 2 parameters in principle: v as a function of time, and omega is a constant. Right? Omega is the magnetic field that's given to it. Let's keep this simple. Whenever we have an equation or a differential equation, we need to have initial conditions, right? Only then there is a meaning to the solution that we're looking for. So let's put in some initial condition to this. Conditions and initial and special cases also, right? So first, let's say this is not initial condition. Oh, let's call it an initial condition. Let's say 0, right? So the 0th initial condition is that this is not really an initial condition. This is a parameter, right? Omega is to be chosen in a way. So omega is, let's say, omega itself times z hat. So you've chosen this to be in the z direction. That's not really an initial condition. Not an initial condition. Even though I write it, not an initial condition. That's a 0th initial condition. Next is what's its velocity, like velocity at time t equal to 0. Let's say it's purely in the j direction, right? So it is 0 in the I direction plus some velocity v 0 in the j direction plus 0 in the k. That's a choice you can make just for simplification. And you should also say what's the position at r equal to 0. Let's say it's at the origin. So the problem will look like you have a X and Y, and Z direction is the magnetic field. So these dots, which represents arrows coming out of the board, that's your magnetic field. Magnetic field is coming out of the board, and right at the origin is your positively charged. Q is positive, let's say. Yeah, didn't specify that, so that's by default it is positive charge. If it is positive, and if it is having an initial velocity in this direction, the force will be QB cross B. Use your right hand rule, it will go to the right. And the expectation is that from our understanding, this will start going in a circle like this. So we should get an equation of a circle as a solution, and whose center is not at the origin, is to the right on the x-axis, and this should be having some radius r, and this is 0, right? And of course z is also 0. And the center of the circle is the expectation is that there is a radius, and we should ask what is that radius, right? What decides that radius? What is that radius equal to? So if I were to, so these are the conditions given to you. What is that radius equal to?
I know what it is based on working with it before, but.
Yeah, that's all. Yeah, I didn't mean anything else.
MV over QB.
MV, so you just, okay, that's probably correct. So MV over, say that again?
QB.
QB. Yeah, I think that's correct. You want MV naught probably.
MV, yeah.
MV naught, so that's here. So that's the same as V naught over omega. Like if you're going in a circle, velocity is omega r. Right, so the cyclotron frequency times the radius r is your V naught. But V naught, once you choose as a max in a circular motion, in this case, this will come out with same. But this is not clear at all. Right? This is this should be our conclusion. So this is from our previous knowledge. We would like to start from these three initial conditions, put it in our differential equation, and we would like to get this as an outcome. And as you notice, I mean, this was pretty much when we do this in the introductory level, we say that, oh, this goes in a circle. We almost say that, oh, a charge moves in a circle. Sometimes there are geometrical arguments given, but maybe sometimes we do differential equation. It depends on how you study this. It's not impossible there. Okay, so let's actually solve this differential equation, right? That's all that is to it. And this shows up at various places, as I said, even when you have a top, like any precision has this equation, right? If you have worked in quantum mechanics with a spin, like if there is a spin and if you have a magnetic field, it will precess around a magnetic field. At top in the gravitational, constant gravitational force, it will precess around. Any precision has the same equation, exactly same equation. The context is different in different ways, but that's all that's going on. Okay, so let's see what this is. So let's say, let's write the three components down, right? So let's say dvx over dt. Before I begin, any comments at this stage on the postulating the problem, if that's what it's called? Okay. Should be pretty straightforward, right, to do this thing. So the x component is right. I will write v as vx plus vy plus vz. So I want the ith component, the x component of this. So x component will be, one will be 2 times 3 and minus 3 times 1, right? So this is 2 times 3, so it is Vy times omega, right? That's the third component, but omega only has a z component. It doesn't have anything else. That's it. There is no next term in there. So if you would expand that out, there is only that much. So that's your one equation, and dvy over dt is equal to, that's a second. So second will be 2, 3 and 1. So that's the 3, 1 is 0 in this case. So minus of 1, which is Vx times omega. Again, you can do this as a determinant and get that however you do that. So that's your two differential equation. And then the third one, which is dvz over dt is equal to 0. If that's true, then this one immediately, you know, that that means Vz is equal to constant. But we also know that initially Vz is equal to 0. So Vz is equal to 0. This constant is actually equal to 0. If Vz is equal to 0, then z remains constant. Right? So that means dz by dt, or not constant, is equal to 0. That means z is equal to a constant. But z is also equal to 0 at time t equal to 0. So z is always equal to 0. So there is absolutely nothing interesting in the z direction. You start from 0 and that stays that z equal to 0. That's it, the xy point. That's the simple conclusion you can make. So you're left out with these two differential equations. And let's go through some. So substitute one into the other. If I were to substitute Vx using this into the other, it is very clear that second derivative of Vx is equal to minus omega squared times Vx. And similarly, second derivative of Vy with respect to square is minus omega squared Vy. That's two differential, in a sense, two independent differential equations, but they're not really independent in the sense that they're coupled using this linear, like a derivative of x is y. So we know solutions for this, right? If you, so this is Vx as a function of time, and these are either sine or cosines. That's what it is. So it is, I don't want to say A and B, right? So because B is the magnetic field there, C, D, E, F, maybe. Yeah, so C times sine omega t plus D times cosine omega t, and we have y of t is equal to, let's say, E times sine omega t plus F times cosine omega t. Very general solution there, but you immediately realize that, oh, that's not as independent as we think, because they have satisfied this, right? So derivative of x with respect to time should give us the y. So if I take the derivative of this, I should get the y. So that immediately gives me some conditions between them. So let's say, let's do that. So derivative of the x with respect to time, that's equal to omega times c times cosine omega t, and minus omega times d times sine omega t, and Vy omega times Vy is equal to omega e sine omega t plus omega f cosine omega. These two have to be the same. These two are constrained to be identical at every time. Right? Each time that has to be true, not just as an initial condition. So that means this has to be equal to this. Right? So we have C is equal to F and E, or F is equal to C, let's say, and E is equal to minus T. So that's one little simpler. So let me write that down. So Vx of t is C sine omega t plus d cosine omega t, and Vy of t is equal to E was minus d, right? So it's minus d sine omega t plus C times cosine omega. At this point, bring in the initial conditions. We have not yet used our initial conditions. Vx at time t equal to 0, Vx at time t equal to 0 is 0. So this implies Vx at time t equal to 0, this goes away, this survives, so d is equal to 0. That goes away. And Vy at time t equal to 0 is actually V naught. So this goes away and this survives. So this implies that C is equal to V naught. Right. Think so. So overall, writing this again, the x of t is C is surviving, so it is V naught sine omega t, and Vy as a function of t is C, so d goes to 0, so C survives, so it is V naught cosine omega t. Clearly says that this implies that Vx square plus Vy square stays a constant in square. It is a signature of uniform circular motion. So that's a suggestive that is a circular motion, but still not very clear. Right? These are just velocities. We just do position, right? We should get a trajectory as an equation of a circle. So this is dx by dt. And that's dy by dt. And integrate this, and we learn that x as a function of time is equal to integral of sine is minus integral of sine is V naught over omega cosine omega t plus a constant right plus yeah. Let me write this as a constant, not the x at time t equals 0. It's just an integral constant here, not really x at time t equals 0. As interpreting that is different. This is just an integral constant. Because at time t equals 0, it's not really 0. So then this has to be 0. Okay. Y as a function of time. Similarly, is V naught plus V naught over omega sine omega t. Maybe I should say C1 and C2. C1 and C2. Again, we can use the boundary conditions at x at time t equal to 0 is equal to 0. This implies that at time t equal to 0, this is 1. So C1 is actually V naught over omega. In fact, that's since it has a dimension of distance and it will come out to be the radius, let's call this R. Let's define this to be the 3-line definition. At t equal to 0, y is also 0. It starts from the origin. So this is 0 now, that means C2 is equal to 0. Okay, so all that gives us the function x as a function of time, x as a function of time is equal to C1. So let me write this as R maybe xt minus R is equal to minus R cosine omega t, right? Because V naught over omega is just R, the way I defined it. And y of t is equal to R sine omega. The way of writing it, and it's written in that form so that again you immediately see that whenever you have a cosine and a sine, square of that should be 1. So that seems to suggest that x of t minus R the whole square plus y of t square is equal to square. And that immediately tells us that that's an equation of the circle of constant radius R. So radius of the circle is R, which is given in terms of the parameters V naught over omega, but as you guys said, this is M V naught over TD. So it's good to think of this as a cyclotron frequency, so V naught over omega. So that's reasonably fundamental there. And the center of the circle, is x is R, I, y is 0, plus 0, and a r dash. What's that? Simple way of looking at the circular motion due to the presence of any questions or comments? All have seen this. Okay. Yeah, okay. Once. Okay, so we saw the forces are as a function of position alone, as a function of velocity alone. So again, Newton's law. Newton's law of motion is mass times EV by dt is equal to some force or the sum of all the forces, effective force, it could be a function of position. It could be a function of velocity. Velocity is by definition the derivative of time, right? So let me be clear here what I mean. Oh, yeah, this is V, where V is or as a function of time. And in general, that could be a time dependence also. Typically, that's the kind of physics we are dealing with. And based on a set of people's work, mostly Laplace, Lagrange, and Hamilton. So from Laplace, they all contributed, I guess, and eventually it was Hamilton. They all, I remember, it's good to realize that Newton was in 1660s. His theory came out in 1660, like he was born in 1642, and probably he was about 23 to 25-year-old when he gave his theory. So it's in 1660s that came out. And Euler was in, so this is Newton. Then there was Euler, who was primarily peaked at 1730 years. Euler. It's not his birth date, but when they're, let's say, most of these people did their best work at the age of 20 to 25. So let's say when they were 25-year-old. Then there is Laplace. Laplace is there. I think, let's say 1770, and Lagrange is around the same time, 1800. And 1850 is Hamilton. Just a historical perspective. The main idea is that before Newton, Kepler had lots and lots of data with him to analyze, and based on that analysis, he could describe the motion of planets. And Newton came and said that, oh, this is governed by these equations, and suddenly there was a huge activity. And by the time Euler itself had a lot of results to show, but very soon they realized that this is a great way of seeing it, but there is some function. It's so it's called a Lagrangian. So we'll define a function Lagrangian, which is a scalar function, not a vector function, which depends on R. Right? And the derivative of R, let me say this is a function of time, right? And then there is the derivative of R, which is basically the velocity, and time t. So they realized that there exists a function for all the problems they were discussing. It was possible with a trial and error to come up with a function which does the following. If you were to call this velocity, that is a derivative of position with time. If you were to take the derivative, partial derivative, because these are now more than one variables, if you were to take the partial derivative with respect to velocity, this should be thought of as derivative with respect to Vx, derivative with Vy, derivative with Vz. So that's three components. That's a vector derivative, if you want. So what I mean here is that d by dr is equal to the gradient. Basically, this is what we say, but now this is with respect to velocity. This is I times d by dx plus j times d by dy plus k hat times d by dz. Right? That's what I mean, okay, oh, I didn't move this. So it was realized that if you were to take the time derivative, so the point is that so you have they realize that all the problems they're working on with after about 200 years of playing around with similar equations, they realize that for all the problems they're working with, for each problem they could come up with a what they call the Lagrangian, whose derivative with velocity and derivative with time was equal to negative derivative with respect to position of L, the same L. So there exists a function L, they call it the Lagrangian, and it was realized that this always happens to be true. Right? And then the point is, why is that? And how do you go around looking at this? And that led to it was very soon, I think this was hints of this were there all the way at the time of Newton itself, Newton and Bernoulli itself, that they realized that this is, so let's call this Hamilton's stationary action principle. And the idea was that you could think of a action, which we'll call using the letter W. And if we were to have an integral of this Lagrangian, whatever we define as L, and it goes from T1 to T2. And you try to minimize it. So when you say stationary action principle, what does that mean? If you have a function, let's say function as a let's say t, right? And if I have some function f here, at this minimal points, we will call those are stationary points, if you want. So that if you were to draw, if this was a position time graph, the velocity actually comes to a stop. Yeah, right. So in that sense, it's stationary. But we will very soon generalize ourselves to extrema points. But that's where this word stationary comes in. Hamilton, because Hamilton played an important role in that. Actions. Why is it called the action? Why is it called action? Anyone? I don't know. Good. Why? What's the essence of the word action? So why is it called? I really don't know why it's called. And it turned out that they realized, or Hamilton, and I would say it has signatures of that all the way back during Newton's time, that you could minimize such a quantity. Then the question comes with respect to what and so on. And you can get this equation, which corresponds to Newton's laws. So what we are going to see in the next few weeks is that what's the connection between this action and what is called, this is called the Euler-Lagrange equation, and what's the connection between this and Newton's law. As always, one-to-one correspondence there, or not, I shouldn't say one-to-one. Lagrangian is not really unique. We will do examples where there's a whole class of Lagrangians which gives you the same equations of motion. So once we have a stationary action principle or a minimization principle, let's very quickly in the last 5 minutes, let's have a simple example, a very similar example, where we see something being minimized. And this is called for this Fermat's theorem. What is Fermat's theorem? Fermat had more than one. So, at least one of them, let's say, anyone. So the idea is that if light goes from one point to the other point, it takes the shortest path. Right? That's one of the Fermat's. Yeah, so let's state that in a very rudimentary, in a different context, let's say. So let's say there is a rectangular box. The rectangle really doesn't matter. It just has to be stratified. That's the only information we need. Let me not make it as a rectangle. Right? It just has to be stratified. That's only need. So let's say there are two regions, and you start from this point here, and your goal is to reach another point on the other side. And here is the rules of the game. You can let's say this is sand. Right? So this is sand, and this is concrete. And of course, if you're on concrete, you can go faster, and sand, you can go slower. So there is a V1 here, and this is V2, and V1 is smaller than V2. And your goal is to start from one point, reach the other. Let's say this is height is the same, h is the same, and you want to get the shortest path. So that's a straight line. If there was no sand and concrete, if it was the same material, you will go take the shortest path, right? That's surely the case. But then here you would say, oh, sand. I don't want sand, I'm very slow. An extreme case would be you are too cautious and you go all the way straight and then go this way. And you will see that that's not really the shortest path. That's you're being too cautious. You understood one parameter and you minimized that, but that's not necessarily the shortest way. This is also not the shortest way. Somewhere in between, right? You want to spend less time here and more time there. So somewhere here is the actual shortest path. And how would you go about doing that? So you would say, okay, I have, this is my, I'll choose my axis here, and that's my x, let's say. And I want to minimize that, right? Or I want to find that x for which time is minimum. So total time t is equal to t1 plus t2. That's what is being minimized, right? Time is going to be minimized. T1 is distance over time is velocity. So this is d1 over velocity v1. This plus d2 over velocity v2. This is height h. Let's say this is, let's call it L, and that will also be L. So d1 is h squared. I need this x, right? So okay, so this is my d1, and that's my d2. The amount of distance I'm traveling in the first, is that clear, my diagram? So this is d1, and that's my d2. So d2, d1 is actually L minus x, the whole square, plus height square, and then you take the square root divided by velocity v1. And d2 is L plus x the whole square plus height square over v2. And this is a function of x. The problem is clear. I want to find that particular x which minimizes my p. And whenever you ask that question, you take the derivative, right? Oops, again, I forgot. I'll take a few more minutes. So our minimization principle is take the derivative with respect to x is equal to 0. Taking the derivative here, so dt by dx is 0. That's equal to, this is a square root function. Taking the derivative, it puts that in the denominator. So that's 1 over v1 square root. So that's 1 over 2. And then I say it's with respect to x. So it is 2 times L minus x divided by square root of L minus x, the whole square plus x squared. And I have to take the derivative of x itself, so there's a minus sign. And this one, similarly, is plus 1 over v2 times 2 and 2 cancels again, so it's L plus x over L plus x, the whole square, plus the height squared. That seems like a complicated expression, but it's not. Notice that L minus x over this is d1, right? So L minus x is this distance over d1. That seems to be, if I were to have this here, and I call this theta 1, right? And this I call theta 2. If you think of optics, right? There is a ray coming in, making an angle. This is nothing but, this statement says that sine of theta 1 over velocity v1 is equal to sine of theta 2 over velocity v2. There is no such, we are not talking about speed of light here at all. That is a human walking there. Let's say some constant velocity c, just to make it dimensionless, and let me call that c over v1 a property called n1, which is suggestive that there is a refraction law there. That's n1 sine theta 1 is equal to n2 sine theta 2. That's Snell's law in optics, right? But we are talking about humans walking around. That's the same principle. In fact, light obeys exactly this principle, that I want to reach from one point to the other point in the shortest way possible. This is stratified, right? There are only 2 mediums. We want to generalize this for a continuous medium, where the speed of light actually continuously changes. Right? That's what we want to do. And that's where the variational calculus comes in. It won't be a 1 parameter problem. It'll be a function we want to take a derivative with. And that's what we want to build up. So it's a simple example. Okay. Thank you. And it took extra time again. But all this should be familiar somewhere or the other, but hopefully brings ideas together. Okay. One. I should make sure I stop it.
Thank you.
Yeah,